Okay, let's get started. It's 10:20. We're picking up from where we left off last time regarding the types of stress or stress states that a material could experience or that you could apply to a material. And so we started with tension. We'll talk about compression as well as shear and torsion in greater detail than where we left off last time. So we went over tension and how the force is applied in this direction, in that direction on a cable, say. So you can see that the length will elongate. So the length will elongate, as you can see here, but that means the cross-sectional area, A naught, will have to contract a little bit to conserve mass. And so we can calculate the stress, the tensile stress, as well as the tensile strain. The tensile stress can be computed by the force or the load that you apply to the material divided by the initial cross-sectional area. And the strain, or epsilon, is just the delta L, or the difference in the length normalized by L naught, which is the initial length. So in compression, it's a similar case, except the direction of the load is opposite that of the tension case. And so we went over the cross-section area, let's say the force of this big rock or boulder sitting on that little cross-sectional area. Okay, so here, if the length is getting smaller, then the cross-sectional area is increasing, right? And this applies for most materials where you squeeze it in one direction, it increases in another direction. Of course, there's always specialty cases where you could have foams with voids, where that might not be the case, because when you're compressing a material, let's say a foam with a lot of voids, it wouldn't expand as much because the material is actually now occupying the voids that were there before. Okay. So while this is generally true, for the most cases, it's not always true, but of course, given that this is an intro class, we'll focus on the cases that are most common as opposed to, you know, all the exceptional cases. And so with shear, right, instead of just having a load that's normal to your cross-sectional area, you could have a component in which the force could be a combination in the lateral as well as in the longitudinal direction. In that case, we call that shear stress and shear strain. Instead of sigma and epsilon, you may have already seen this, where it's actually tau and gamma. Now, this is not to be confused with tau, the relaxation time of a polymer after we've applied a stress in for very particular cases. So we'll go over the properties of viscoelastic polymers where there's also a tau involved. So clearly you must take it within context what the tau actually represents. And so just like the tensile and compressive stresses that a material could experience, where it's force divided by the cross-sectional area, with shear, it's also F over A naught, where A naught is the initial cross-sectional area. But now the strain has an angular component to it, right? So it has this component where it's opposite over adjacent, so it's tangent of this theta. And so the applications where you would need to consider shear strain and shear stresses are these conditions where you could potentially have two materials, this A material and this B component could be the same material. But if the force is loaded this way and this way, there's going to be some shear associated with the stress and strain that this bolt right here could experience. Similarly with torsion, right, you could think about the same ski lift, and instead of just looking at the cable, you could think about the other components of the ski lift where it would experience not only a normal force, but also now an angular component. So very similar to shear stresses and strain, the torsion stress and strain can be computed if we know what the angle of displacement actually is. Right. And of course, in real life, when we're testing materials, what we try to do is one of these particular measurements where we try to isolate either the angle or we take it into account. And so if you've ever done an experiment where you're actually trying to pull apart a material to look at the stress strain curve that we've looked at, you probably have done something like this, where you've, prepared a sample that looks something like this, sort of like a dog bone style type sample, where you have a specific gauge length here. And what you really want to do is engineer it in a way that the material will fail within that length. Because what you don't want to do is you don't want to induce a situation where the material will fail where it's being gripped, let's say here or here. And so by designing the sample specimen this way, you make sure that it fails somewhere within the middle here. And you can put devices on it so that it will measure the elongation for you and track it for you. And so all of these are outlined in by the American Society for Testing and Materials, or ASTM. Now, you may have used it already by looking up, certain parameters like elastic moduli or yield strength. So you probably would have, looked in this database already if you've done research in, let's say, a metallurgical group or industry where you're trying to optimize, for a certain property. And you could see that this could be human dependent, right? If someone is loading a particular sample in a certain way, how do we ensure that when we buy a certain composition of material, a certain composition of metal, that it will always have, the yield strength that we expect, or the tensile strength that we expect, or the stress at fracture that we expect, right? And if you think about the cases that we just talked about, ski lifts, or anything that involves transportation of people, right? These parameters are absolutely critical when we're trying to engineer for these end uses. And so the ASTM regulates how these tests are done so that as a manufacturer, you can ensure your measurements are in line with everybody else's measurement. And as a consumer, that when you buy a piece of material, that it falls in line with whatever regulation it is that they have, and that the number is actually reliable. Yeah. And so this is done pretty commonly for materials that are mainly metals. We'll talk about how when you have ceramics and polymers, they don't behave in the same way. They're not as ductile. So engineering ceramic materials where you want the material to fail right in the middle there is actually extremely difficult, because either you clip on the ends of the specimen, or you have to screw on. As you can see here, there are screws. So you can screw on the specimen onto the load frame. And so with metals, this can be done with great accuracy. With ceramics, what tends to happen is as you're even putting in the screw, your material can fracture quite easily. And if you don't design the screw correctly, it won't break down the line, right? What you really want is you want to be able to pull the specimen and have it break right in the middle. And so what will happen is your ceramic material will just actually break where the screws are, where the material is actually attached to the load itself, and thus rendering this measurement pretty useless, and thus also not good use of your time. Okay. So when we do these measurements, in terms of testing, let's say tensile stresses, we're really delineating the elastic region from that of the plastic region, right? If we apply a load and we release the load, in the elastic region, we can get the material back. So the deformation is reversible. And we can measure things like Young's modulus, or the modulus of elasticity. We can measure Poisson's ratio, so how much does a material expand and contract? The yield strength, as well as the resilience. Right? So that's the energy absorbed in the elastic regime. Beyond the elastic regime, where you've induced enough deformation so that it's not reversible, right? Well before fracture, we can measure its tensile strength or ultimate tensile strength, ductility, so how much, how malleable is this material going to be, and also toughness, right? So in thinking about, if you're the designer of, say, like the F-150, and you think about designing a chassis that can absorb a lot of impact, right? You don't actually want your material to just fracture upon impact, right? You want that body to actually absorb a lot of the energy so that it deflects it off of the passengers that are inside the car itself, right? You need to pick materials that have high toughness, but also high ductility, right? So these are the things you want to think about for these particular cases. Given that this is a material science course, we're going to not only look at the mechanical properties but we're also going to look at where does that mechanical property originate from, right? We can go back to that bond energy curve from chapter 2. And when we think about the bonds in a system and where atoms are, we've been talking about equilibrium states, right? We've done a lot of work on calculating how there's a preferred interatomic distance where the energy, the potential energy is at a minimum, right? So here you see all the bonds drawn as little springs here. They're all connected, they're all equidistant. All the atoms are equidistant to each other. So when then you apply, let's say, a tensile load, and then you release it, what happens is you stretch the bonds. So here you see elongation in the bonds uniformly, okay? But you're not breaking the bonds. So imagine these are metallic bonds. They could also be covalent bonds. But you're applying some deformation, but the bonds are staying intact. You haven't broken any bonds just yet. The system may be at higher energy in terms of the potential energy well that we've been talking about, but it's still a state that you can access. Okay. So then when we talk about stiffness of materials, when we're operating in the elastic regime, we haven't broken any bonds yet. When we release the load, the material can come back to its original state. We can think about then, what does that mean when we're comparing different bond energies in this elastic region? So I'll remind you about the bond energy curves that we talked about, where we looked at the second derivative of the energy curve. So the first derivative is force, the second derivative is the curvature, and that gives us a sense of how stiff or how strongly bonded these atoms are to each other in a material. So here you see the blue curve and the red curve for the bond energy as a function of interatomic distance r. And so when we take the first derivative, we get dF, and that's shown in this plot here. And then when we take the second derivative right at the equilibrium interatomic distance, R naught, so it's dF dr at R naught, we see that we have two different slopes. And these slopes, the value of these slopes, or the magnitude of the slope, will tell us the strength of these bonds, right? So the red one will be stiffer versus the blue curve. Okay. So of course that all has to do with the elastic moduli of a material. And also in the linear regime, we can relate the stress and strain with the Young's modulus, shown here as capital E. So it takes on the form that you already recognize, right? It's a slope. So knowing the relationship between stress and strain, given that it's related by the modulus of elasticity, or Young's modulus E, we know that looking at a stress-strain curve like this, that we're really talking about this region, right? Where we can sort of eyeball a linear line of some sort. So you must wonder, where does this line end, right? Where do we consider the elastic region, and then where does it stop, so that we go on and we enter the plastic region, where deformations are not reversible, okay, where you're starting to break bonds and reform bonds. So we'll talk about that, but for now, let's just assume you can eyeball some linear slope like this. Okay, so it's just rise over run, stress over strain, sigma over epsilon. And we can compute a relationship between the elongation as well as the change in the lateral direction of a material with Poisson's ratio. So this ratio tells us that the strain in the lateral direction divided by the strain in the longitudinal or axial direction is going to vary between 0.25 and 0.5, sometimes 0.4. And this just gives us a good sense of what regime we're in. So metals tend to be have a Poisson ratio of 0.33, ceramics 0.25, so polymers 0.4. So what is this telling you? It's telling you that as we go from metals to ceramics to between metals and polymers, say, right, your Poisson ratio is increasing. What that means is your lateral, your numerator, is changing by quite a bit, more so than metals. Okay. We could also write out relationships for the shear modulus, G, as it relates to the shear strain and shear stress. So that's just now tau is equal to G times gamma. So we're still operating in the linear regime. Okay. This linear regime being the elastic region. So it does not pertain to the plastic region at all. So I talked a lot about metals, right? That's obviously quite a mature field. There's a lot of data on all sorts of metals that you can think of. You can also think about doing these measurements, obviously, for polymers. You could also think about doing it for biomaterials. Here you see a stress strain curve from this 2015 paper on fragility of bone. Clearly, your bone is much more brittle than that of your tendons, which we already have an intuitive feel for, because whenever you break your bone, right, people don't really talk about breaking your tendon per se. You stretch your tendon and you pull it and what have you. But that all has to do with its properties, right? Bones are made of what? Calcium, not the metal, calcium. The 30% BME folks in the room can shout it out. Calcium phosphate. Okay. Oh, I heard an O. Okay. I don't know what that O was about. But if you knew, shout it out, right? So it's a ceramic type material, and you can see here that, well, it's a number of things beyond calcium phosphate. That's the majority, but it's not all calcium phosphate, of course. But basically the point is it's a ceramic type material, so it's stronger, but it's more brittle, right? Whereas tendons, here you see if we estimate the yield strength, and we'll define exactly what the yield strength is, but let's say we eyeball it, and we're not following ASTM convention. Let's say we eyeball it and it's here versus here, right? So bone is stronger, but more brittle. Tendon is less strong, but you could see it can absorb, it's more ductile, and it can absorb more, more energy, more of the impact, okay? So it's a tougher type material because you need a larger energy to break it, okay? So then if we look at elastic moduli for different types of materials, so we're looking at this slope in the elastic region, stress over strain, we could see some generalities here, right? We can see that metals in this red box right here, tungsten, molybdenum, your steels, tantalum, platinum, copper alloys, and so forth, generally are higher, so they're stiffer than that of, let's say, polymers, which are magnitudes lower. And then you also have comparable numbers for ceramics. So you have diamond all the way at the top, but graphite, its allotrope is at the bottom end here. And then you have a whole bunch of composite materials. So we'll go over what all these acronyms mean in the composite section and how we can engineer basically some sort of averaging effect to basically make the best of, take advantage of two materials by making composites. We can also look at the tensile strength. So this is the highest stress that the material can experience. So that's the maximum on your stress strain curve. We can see here, generally it's about the same. Metals are here, ceramics and semiconductors are about intermediate, and then polymers are much lower. And of course, composite can run the gamut, because we're going to talk about how they're made up of two types of materials, or more than two types of materials, actually. Okay. So we can do a sample problem where we're asked to calculate the stress strain, use the values of the stress strain curve to calculate some mechanical properties. So the first part is, how do we calculate the elastic strain epsilon of a sample of steel if we know its elastic modulus is 207 gigapascal, and that we've applied a stress load of 20.7 megapascal? Well, it's asking for the elastic strain, so we know this is a linear relationship, right? We know that the elastic stress is related to the strain by the Young's modulus, right? So if we're asked to calculate the strain, then we know that it's just stress applied divided by the elastic modulus, which is 207,000 megapascal. So I just converted gigapascals to megapascal because strain is unitless, right? So be sure to convert your units. And we get something that looks like this. So the strain is 1 times 10 to the negative 4, or 0.01% strain. Okay. So what that's telling you is the amount of elongation in your material, delta L, normalized by its initial length, L naught, is 0.01%, or 0.0001. Okay, that's the strain. So then, if we're actually given dimensions of the starting point, so what is then the resultant length under this stress if the original sample is 1 meters? Actually, I think it should be 1 millimeters, but we can calculate that now that we know the strain, right? We know delta L is just the final length minus the initial length normalized by the initial length itself. So we can plug in what so we can calculate the resulting length, L final, by manipulating the definition of strain as well as the relationship between stress and strain of a material in the elastic region. Okay. And then if we're given a Poisson's ratio of 0.33, and we know that the diameter is 1 millimeter to begin with, so we know what our D naught is, we can use the relationship of Poisson's ratio is the strain in the lateral position divided by the strain in the axial or longitudinal direction. We know that the lateral position will start off with some diameter, d naught. In this case, we're given 1 millimeter. And we want to know what the change is, delta D. We already know that this is delta L divided by L naught. And so what we're really rearranging for is this delta D. Okay, so the new diameter. Since this is tensile, we know it's going to contract. So our delta D is actually going to be D naught minus D final, because it's contracting. Okay. So the new diameter, what we're really solving for is this D final. And we have the numbers for everything else. Okay. The algebra I'll leave to you. Any questions on this specifically regarding the strategy? Well, since there are no questions, I'll give you a little side note. Here, I've given you, you're able to calculate epsilon, right? Since you're given the applied stress. If you're given load instead, let's say the force that you're applying to this material and the initial cross-sectional area, A naught, you can compute what sigma is if you're not given sigma. So in this particular question, you're given what sigma is. But if you're not, you have to be given information about the load, F, and the original cross-sectional area. And there you can compute the load, okay? So most likely what will happen is you know the force that you're applying to a material. You can measure the diameter of your specimen if it's a cylindrical sample. So you can plug in those values, right? Your force is pi r squared. So if you know the diameter, you can just take a caliper to your material, right, to your specimen. You can measure your radius, and you can compute the stress that way. This might be useful for one of your homework questions. Okay, now let's go over the definition of yield strength itself. Before I said, let's eyeball a linear region. If everybody did that, we would be all over the place, right? There wouldn't be a standard protocol for measuring yield strength. So the exact definition for when your material starts behaving from elastic to plastic is where we define what's called the 0.002 offset. Okay, so what does that mean? This means in your strain, in the x-axis, you go over 0.002 if it's reported in fractions, or 0.2% if it's reported in percent change. And you draw a line with a slope that is the same slope as this region right here. And where it intercepts your stress strain curve is the yield strength. That is the definition of yield strength. Now, atomically, what has happened is before you even get to the yield strength, before you even get to this point right here, realistically, what's happening in your material is that the atoms are starting to shift already, right? So like say here, you already see deviations from linearity right here. So why wouldn't the yield strength be right there, right? Well, atomically, we can't really see that. So the standard convention as deemed by the ASTM is that you go over 0.002 strain, and then you follow the slope, and where it intersects, that is the definition of yield strength, okay? Obviously, as soon as one atom, two atoms, a whole plane starts moving, it's starting to propagate the plastic deformation. But even with advanced microscopy these days, we can't exactly and reliably and uniformly say this is it, right? So this is our standard definition for now, okay? So that is the convention. You look at the plastic strain, trace the parallel slope, and record that value, even though we can look at the stress strain curve and say, well, there's already deviations from linearity well before that, okay? And here are the yield strengths for different material. You could see that that value is difficult to measure for ceramics for the reasons that I've already talked about, that it's actually difficult to make a specimen to even test the yield strength. Okay. In the interest of time, I will do this example where if you're looking at a stress strain curve and you're asked to calculate its yield strength, you don't actually calculate anything, right? You actually just go to point, this is reported in percent, so we go to 0.2% by convention. We draw the line where it intersects the stress strain curve. We read that off as our yield strength, and that's 325, not 250, because if you were eyeballing it, you would say, well, that also makes sense, right? That's about where the linear region ends, and you would be wrong by convention. Okay. Okay. Tensile strength. So this is figure 7.11 in your book, where we can read off the tensile strength as the maximum stress that the specimen experiences. This is where what's called necking occurs. So we've talked about ideal cases where you made a specimen of known geometry and starting aerial cross-section. As you elongate this material, this region right here starts to get smaller and smaller until fracture. And the point of fracture is where your stress strain curve data stops collecting, right? Because your material has now fractured. So for metals, they can be ductile. And here, when we talk about the ductility of a material, we're really talking about percent elongation after plastic deformation or reduction in the area. What you see in the literature more so is this value, where we measure the final length minus the initial length L naught and normalize by the initial length itself, multiplied by 100. So that's the percent elongation. So you can see that, and this starts to look like epsilon, right? If epsilon is L naught, or sorry, delta L divided by L naught, but percent elongation is multiplied by 100. You could see here, this material in red is more ductile than the brittle material, while the blue material is stronger. So the yield strength is, you know, if we, x-axis doesn't have any units, but we can see, right, that the yield strength here is greater than the yield strength here, say. So there are two distinguishing features when we talk about ductility. When we talk about the strain, right, we're talking about at point of fracture, we can read the value by just going straight down, just drawing a straight line down and reading this strain value. I call this C prime in this particular plot. So that's your strain at failure. But when you release the material, right, let's say the material fractures, there's some component of elastic recovery. And in that case, that is, you know, that part here. And so here then, if you read the value off of the x-axis, there, that's the plastic strain at failure, because you recovered some of the elastic region right at failure. Okay, so if you know you're in industry and somebody's asking you about strain at failure, you're really telling them this value right there versus the plastic strain at failure, which you would have to draw a parallel slope of the elastic region and then read off that value. Okay. Okay, more technical terms, resilience. When we talk about the resilience of a material, we're talking about its capacity to absorb energy, but only when it's deformed elastically. We haven't entered the plastic regime yet, right? We haven't entered the regime where we deform the material in a way that is not recoverable. It's still recoverable at this point. And so if you're looking at this, you're thinking, well, it kind of looks like a triangle, and that's exactly how you would compute it, right? You can do just simple base 1/2 base times height for the area under the curve, right? That's the energy that's absorbed by the material. And that's worked out to be the square of the yield strength divided by 2 times the Young's modulus. Okay, so that's pretty simple. What's less straightforward is toughness, right? When we're talking about the energy, we're talking about the integration under the curve. And you can imagine, let's say for ductile metals, the toughness of a material, you'd have to integrate the area under that curve. And it's not as straightforward because there's no analytical form for this stress strain curve, right? So what you can do is you can just do numerical integration where you can treat this as, you know, that triangle. That's pretty easy. And then you can fit, let's say, a polynomial to the rest of this curve, right? It could be something to the 4th, something to the 6th. You fit a polynomial and you can just integrate that curve. And so you can see here the toughness of, let's say, ceramics, so the area under the curve for ceramics versus for ductile metals versus for polymers is obviously quite different. Right? So while ceramics have high strength, they have low ductility, and they also have low toughness because the area under the curve is not as big. That number is not as big as, let's say, metals. Okay. Now, let's dive into plastic deformation. Atomically, what's happening? What's happening is you have plastic deformation where here's the initial state of atoms, right? It looks pristine, everybody's packed, maybe even close packed, say. When you apply a small load, there is plastic deformation, and your load is actually in tension, so it's going this way. So in the cartoon you saw before, atoms are, the bonds are elongating a little bit, but everything is still reversible. Then let's say you apply a larger load, right? The stress is greater now. What happens in the material is that bonds will actually get broken, and then there will be a shift of atoms in the plane, and then new bonds will form again. So you have some elastic component and some plastic component, but it's not reversible because you've originally broken some bonds, and even though you form new bonds, you could see just from this cartoon right here, it doesn't look like this cartoon right here, right? So even though your material hasn't fractured and ruptured and all of that, it's still irreversible deformation because you've broken some bonds, but other bonds have reformed. So atomically, what it looks like is this schematic right there. Okay. So that's the atomic difference between elastic deformation that's recoverable and plastic deformation that's not recoverable. Okay, so here is a link. A link to the Wheel of Death. So what you should see upon loading is a titanium specimen loaded, and you can see the fracture will happen very quickly. So you see here, it's being loaded. You should see some elongation, you see some necking, and then that's it, and then there's fracture. And then the camera work is very terrible and jiggly, so we're going to exit. Not everybody, has a focus on cinematography here, but it gets the point across, right? And when you hear this pop, actually, what will happen is that's the pop that you hear is actually the energy that is released. And so for certain materials, if you hear a small pop, that's not a lot of energy. For certain steels, you'll hear a large pop, in which case that's a lot of energy. And for certain materials, you shouldn't even be in the same room when the pop happens because it is quite deafening and detrimental to your eardrums, right? So that gives you a sort of physical sense of the energy that is released or that material can absorb, and gives you a sense of the toughness as well. Okay. So here we see elongation, some stretching, and then all bonds being broken and then reforming, and not in a reversible way. Okay. I think I've actually said all of this, but this just drives home the point that what's happening at the neck, like where that region gets smaller, the material is actually getting stronger, but you wouldn't know it if you plot it in this style where the stress strain curve is normalized by the original length, the L naught. If you were to actually instantaneously measure the cross-sectional area and the elongation of any given time, L sub I, so instantaneous, not L sub I is initial. I realize that's confusing, but the notation in your book, that's what they use. Any instantaneous length, when you measure that, if you normalize by L sub I versus the original L naught, you get something that looks, more like this, and you see that your material is actually getting stronger right in the neck region. That is more laborious, and actually it takes higher end equipment to actually be able to compute that. So the traditional stress strain curves that you see in databases looks more like this one, where it looks like your stress is going down to the point of fracture because you're normalizing by the initial cross-sectional area and the initial length versus the instantaneous length. Okay, so that's the difference between engineering stress versus the true stress of a material. So in the neck region, it's actually getting stronger. Okay, so that's what this curve shows. This is the true stress right here, but what you see reported is actually the engineering stress. But you can compute that by relating the total strain to the true strain in engineering strain. Okay. We're going to jump over to ceramics before we get to viscoelastic polymers, which I'm pretty sure a lot of you have dealt with in your life. Viscoelastic polymers, the silly putty being the most wide known and commercially viable viscoelastic polymer. So you were doing material science, at the age of 3. But before we get to that, let's talk about ceramics and their behavior mechanically, right? We can talk about ceramics in a number of ways. We can talk about ceramics in their powder form, the polycrystalline form. We can talk about ceramics in their single crystalline form, and both, of course, have wide uses. So polycrystalline alumina versus single crystalline alumina or sapphire. Interestingly enough, so sapphire is obviously a gem that you can buy. Interestingly, does anybody know what chromium doped alumina is? So it's also alumina based, but now you doped it with chromium. Well, nature has figured it out. If you've ever bought ruby, right, it's the red gemstone. If you ever bought ruby, what you're really buying is Al2O3 and in its single crystalline form that some jeweler has cut down some facets. Which facet you should ask? Well, you should review chapter 3, crystal structure. They cut along certain facets and they sell it to you for a lot of money when it's really just Al2O3 with a little bit of chromium doped in there. And it's because, you know, in the dirt, some chromium got into aluminum, and that's all there is to it. So clearly, what you're really paying for is this. You can buy aluminum oxide for like cents on the dollar, by the way. Or if you leave aluminum out, like a sheet of aluminum foil out, over time it's going to oxidize. There's always a passivating layer of aluminum oxide on the surface. That's essentially what you're paying for, by the way. So same thing with sapphire emerald as well. It's doped with other 3D transition levels. So I guess what you're paying for is the gesture that maybe you care about somebody. Okay, so let's talk about now mechanical properties as opposed to the economics of alumina. Let's talk about how we can test. Let's say you have a single crystal sapphire, or you have ruby that somebody gave you. You can actually test the mechanical strength of the mechanical properties of these ceramics, but it's difficult to do so because the material will probably fracture before you get to meaningful numbers that we've just gotten for metal systems. Okay, so instead of talking about ductility in these in ceramics, what we talk about is actually flexural strength or modulus of rupture. Okay, so we talk about the stress at fracture within these materials. And so you may have seen this diagram in your statics course where you can do 3-point bend test or 4-point bend test, right, and get out the flexural strength or the sigma sub F as you see here. Okay, so what typically happens is they'll fracture well before any ductility happens, right? That's why you don't see this type of curve for ceramics. And so depending on if you have a rectangular geometry or cylindrical specimen, we can calculate the flexural strength or the stress at fracture for these materials to get a sense of its mechanical properties by just knowing the dimensions of the specimen itself. Okay, and so we can compute that by just looking at the dimensions and the moments of inertia. And so if we look at the stress, it's just the maximum bending moment divided by the moment of inertia cross-section. And so for rectangular cross-section, we get this relationship where it's 3 times the applied load, F, big F, times L, the original length of this specimen, divided by 2 times B times D squared. So really just the cross-sectional area. And we can do the same thing for the circular cross-section and get some analog for that cross-section. So this example I will leave for next time and come back to it, or I'll upload a tutorial video on how to calculate the modulus of rupture and determine whether or not something will fail. So basically you need to calculate what the stress is, and if you know its stress at fracture is a certain value, above or below. So above it will fracture, below it won't fracture. All right, we'll pick up here next time on viscoelasticity of polymers.